So there are there are four possible combination. You can have two capacitance, you can have one capacitance, one inductor, you can have one inductor, another capacitance, you have one inductor. So when you want to transform high values of impedance, as in the case shown here, this Zn is 50 and RL is going to be some 5 or 6 ohms. Here I am reducing the value. So L1, C1 I'm going to use. But see, when you are going to transform the resistance to higher value, you can go for this capacitance based network. So I'm going to have two capacitance C2 and C1. So so I can analyzing this network is going to be difficult. So what I'm going to do, I'm going to convert the C1 RL parallel into C1 RS series. Okay, so C1 RL parallel is converted into C1 RS series, and you know C1 in series to C2, I can replace it by C equivalent. So it becomes C equivalent into R total. So I can find the expression for the C equivalent to C1, C2 by C1 plus C2, and R total is going to be 1 by RS into C equivalent omega square. And if you simplify, you get this expression R total equal to 1 plus C1 by C2 the whole square into RL. By choosing proper value of C1 and C2, I can boost the impedance of my network. So that is the network boosts the value of RL by a factor 1 plus C1 by C2 the whole square. You can see RL into 1 plus C1 by C2 the whole square. So it is going to increase the value of your, boost the value of RL from RL to this multiplicative factor 1 plus C1 by C2 the whole square. So note that the capacitive component must be cancelled by placing an inductive component in parallel with the input. So definitely when you have a fully capacitive network, it is going to introduce its own drawbacks. So for that, you definitely have to include one inductor in the circuit to cancel out that effect. So by including that, you can cancel out the effect of the capacitive component. And for this circuit, if you find, when all components are in parallel, you don't find Z, you will be finding admittance Y. So when you find the expression for Y, you get this expression. So same way, find the real part of your Yin. You will get the real part is going to be this one. So R total equal to 1 by real part of Yin. So you get this expression. So from our understanding, it is very clear that four L section topologies are possible. As I told you, either C1, 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 C2, L1, C1, and series L1, C1 in shunt, and both are going to be inductors. So these are the four different topologies you see. So in figure A, C1 transforms RL to a smaller series value. So see here in figure A, the input resistance is less than your load. This is one case. This is also, you can see here, input is less than your load. So whenever you are going to have a series component first, that side impedance value is going to be less. Okay, please understand it like that. So see here I have L1 in series, C1 in shunt. So the input impedance is less. Here I have C1 in series, L1 in shunt. So input impedance is less. But here you see I have C1 in shunt and L1 in series. So series with the load. Okay, so load value will be less, or I can say the input impedance is large. R in Z in greater than RL. So same way here, L1 in shunt and C1 in series. So I can say the load value is less, or the input impedance value is going to be large. So depending on what value you are going to transform, definitely when you are going to design impedance matching networks, one side will have larger impedance and one side will have smaller impedance. For any of the scenario what we require, we will have a pair of solutions. Because you see, for less than case, you have two solutions. For greater than case, you have two solutions. Among the two circuits, you can choose which one is better by performing simulation, and then which one is having the necessary characteristics, we can use that for our final implementation of the circuit. Okay, so that is possible. So for any problem, we'll have two possible solutions, which is evident from the circuit diagram, whatever you are seeing now.